Hello folks, welcome to another Lab in Theory tutorial. In this video, we'll be looking at some basic linear regression and how to code up a problem in MATLAB. We'll look at how you can start off with a model, linearize it, and then fit some experimental data to it. So the particular model we'll be using today is called the Antoine Equation. Now, this equation is probably most familiar to chemical engineers, but it's a simple relationship between the vapor pressure and temperature of a compound. When the vapor pressure matches the atmospheric pressure, a liquid boils. Now, let's take a look at the wiki page. So, as you can see here, the Antoine equation is a very simple model. It has three parameters, A, B, and C. In its current form, it's nonlinear, but we can linearize it pretty easily. So let's do that. Now, let's get started by writing out the Antoine equation. So the Antoine equation is log base 10 times P, which is the pressure, is equal to A minus B divided by T plus C. So our main objective is to linearize this equation, and we want to linearize it with respect to the parameters A, B, and C. So the first step is to multiply out by the denominator so we can isolate the t away from the c. And let's see what happens. So what I'm going to do is I'm going to drop this 10. So the log I write from here on out is log base 10. So we end up with log p times t plus log p times c is equal to at plus ac minus b. Okay, now the next step is we want to divide everything by t, because that way we can isolate the coefficients of each set of unknown parameters. So by doing that, we end up with log p. I'll leave this on the left-hand side and set everything else equal to, and then the first thing we then have is a, and then we have plus, and then I'm going to isolate out ac minus b, and then this is all times 1 over t. And finally, we end up with minus c times log p divided by t. Now, our three coefficients in this case, if we were to write this in the form of y is equal to a naught plus a1 times x1 plus a2 times x2. The a naught is the first coefficient, a, which is unknown. A1 is ac minus b right here, which as well we don't know. And then finally, a2 was minus c. X1 we can calculate with some experimental data, and that's just 1 over t. X2 will be log p divided by t, and y, of course, will be log p. And with this, we can take this final form of the model and we can linearize our data and then perform some linear regression in MATLAB to identify A, B, and C. So let's take a look at doing that. In our practical example, we'll be looking at some basic data for ethanol that I have here in a Excel spreadsheet. So the data is very simple. We have two columns with a number of temperatures and corresponding vapor pressures. So let's take a look at two separate ways of importing this data into MATLAB. The first is a simple copy and paste. So I'm going to take this data, I'm going to hit Control C, that's going to copy the data, and then I'm going to go to MATLAB. I'm going to assign this to a variable, I'm going to call it A, and then I just open a square bracket and then Control V to paste the data, close the square bracket, and then I'm going to add a semicolon and hit Enter. And you'll see that I have a new variable called A in my workspace. And MATLAB's pretty smart about preserving format when it comes to copy and pasting data. This approach is actually quite nice if you don't have too much data, or if you're lazy like me. I don't recommend it if you're trying to develop a workflow or do anything reproducible, but it's handy if you just want to do a little bit of quick analysis. Now, the second approach is to actually import the data using a built-in MATLAB function. Now this function, it's called XLSRead, so B equals XLSRead, open a parentheses, and just a note about this function, it actually works best on a Windows PC. I'm not sure how it behaves on Mac, but there are definitely some compatibility issues, especially with these the new excel.xlsx file format on Linux. Anyways, let's import it here. So ethanol, I'm going to hit the tab key and it auto completes it for me. I'm not going to pass in any other arguments, and I'm just going to hit enter. It takes a moment for it to process, but once it does that and it returns, we'll see what it gives us. Now, notice right here in the workspace that I'm just going to increase this value right here. What you'll notice is that it's of size 15 times 2, which is the same as the matrix A. So A is that, and B is the same thing as well. It's identical. Now, the import command, the XLS read command in MATLAB is pretty smart. It notices that in the first 2 rows, there's no number data. And so it'll just ignore those and move on to the rows and columns that contain, or the rows that contain data. Now, what happens if you have a row that contains text, for example, and some data? What'll happen is MATLAB will throw a NaN in there, or a not a number, and it won't fill it in, but we'll talk about that at a later time. So I'm going to clear my screen. Let's take a look a little bit at the data we imported. What I'm going to do is, to make things a little handy, is assign T, so temperature, to the first column of the A matrix. And we do that by saying A, and then we use this colon operator, which means everything in this. And in MATLAB, it's row first and then column. So we're saying select every row and the first column. I'm going to ignore that. And as you can see, T now is just a bunch of temperatures. The next thing I'm going to assign is P, and I'll set that equal to A, colon, comma, 2, and then hit enter. And now we've imported our temperature and pressure, and we've assigned them to some useful variable names just to improve our readability. Looking at the linearized Antoine model, we want to define some MATLAB variables to represent it in this format, which is y equals a0 plus a1 x1 plus a2 x2. So the first thing we do is we assign y, that's equal to log 10 of p. So MATLAB is case sensitive, so you want to use an uppercase P. And the other thing is that if I do not type 10 here, simply log is the natural log, and the Antoine equation, or the Antoine model, uses log base 10. Now, the next thing is actually x0. So x0, so remember, in our model, in our linearized model, we have a0 plus a1 x1. But x0 in MATLAB would end up being just a vector of ones, because this is multiplied by just a bunch of ones, if you can think about each data point being an entry in a vector. So we can define this as typing ones, and then we will say length of t, because we want it to be the same length as our temperature or pressure entry, and then 1. And this will create a length t by 1 vector. Hit enter on that, and then immediately you can see we have a 15 by 1 double. Now, x1 is equal to 1 divided by t. Notice the use of the dot operator for element-wise division, and x2 is equal to log 10 p dot divided by t. Again, element-wise division. Hit enter. Now, the next step is we want to set up the form ax equals b to solve the system of linear equations. Now, a, I will override the old a variable, but I'm not too worried about that right now, is equal to x0, x1, x2. I'm going to hit enter. Notice there's our a. And then b is equal to y. So we looked at this before, but to solve this system in MATLAB, we simply use the backslash operator. So x is equal to a backslash b, and we have a solution. Now that we've solved the system of linear equations, or more precisely, we found a least squares solution to the system of linear equations, we'll talk about that a little bit more later in depth. What we want to do is extract the Antoine equation parameters a, b, and c from x. To do that, we go back to the linearized model. Taking a look at it right here, we notice a couple of things. Immediately, x1, the first element of x, which is our solution, gives us a. The third element gives us minus c, and then we can use the two of those to get at ac minus b and finally obtain the value of b. Going back into MATLAB, I'm going to use a prefix of a for Antoine, so aa is equal to x1, and then AC is equal to minus x3, and finally AB is equal to AA times AC minus x2. Now that we've extracted the three values, which are 5.25, negative 46.1, and 1601.3, let's compare how we did to the actual NIST published data. If we compare the model parameters we've obtained using the linear regression in MATLAB to those published by NIST for the Antoine equation, we can see that our values fall squarely in between these two published data sets, which is actually not bad at all. So the final thing we have to do is to just plot our data and our model and see how well they compare. To do that, we'll use the built-in plot function in MATLAB. We want to plot temperature, pressure, and then I'm adding a little O here. And what that essentially does is it will plot this data as a bunch of open circles on the graph so we can compare it to the model fit that we've obtained. Next thing we do is I want to plot temperature once again, and then recall in the Antoine model, it is log 10 of the pressure, and in order to plot the pressure directly, we'll take 10 dot to the power of, again, element-wise operation, AA minus AB dot divided by T plus AC. And then make sure we close all our parentheses, hit enter, and there you have it. A beautiful fit to our data using the model, simple linear regression in MATLAB, the backslash operator, and we get a fantastic fit to our experimental data. I hope you found this tutorial useful. If you've liked it, found it helpful, please give it a thumbs up. If you want to see more of the same stuff, please subscribe to my channel. And of course, as always, leave your comments down below. Let me know what you're interested in learning about and seeing in MATLAB, and we will be more than happy to produce a tutorial for you.